So welcome to the next lecture. Today we are going to be talking about model based control approaches. Model based control approaches, and why do you want to use such approaches? See, PI or PID control will actually give you the desired control performance in 90% applications. There are, however, let us say around 10% applications where the tightness of control achieved is not acceptable for various reasons, and it is in these situations where one should consider model based control approaches. A very pertinent example for chemical processes is if your open loop transfer function has got a large dead time, you can't get tight control because the dead time creates a lot of phase lag, and therefore the gain at which the control loop goes unstable is quite small, and therefore you are stuck with using small KCs, and if the KCs are small, well, the loop is slow acting or not as tight as you would like it to be. So one of the first, this was probably meaning the Smith predictor. The Smith predictor was probably the first application that you may call as the precursor to formal model predictive control or model based control. And what is done in a Smith predictor is consider a first order plus dead time process. So here is your first order plus dead time process, k e to the power minus theta s upon tau s plus 1, where theta is quite large, probably larger than tau. That means the dead time is significant. Okay, so this is your process. Now and of course there could be a disturbance that comes in, and this is your output y. What is done in a Smith predictor is, this is your input to the process. You take a model. So this is your process. And what you do in this model, k, let us put a subscript m to indicate model divided by, so this is your model of the process, and what you do then, subtract the prediction of the model, which is, let us call it y hat, from the actual measurement y, and what that gives you is an estimate of the disturbance. Okay. What you also do is take the easily controllable part of the model. You see, controlling the full process model with the dead time in there, well, you can't do it real tight. So what you do then is control the easily controllable part or the tightly controllable part of your process model, which is only the first order part. Okay, so this is model, and this is the truncated model. What do you mean by the truncated model? Where you have truncated that part which is giving you control problems. So in this particular example, the part that is giving you control problems is dead time. So removing the dead time, what I am left with is km by tau ms plus 1. So that is what I have here, and what I do then is send it to a controller, which could be, for example, a PI controller. This is a PI, let us say it is a PI controller, okay, plus minus, okay. I also have a set point for y plus, there is another feedback loop here, minus, okay. This is the Smith predictor. Now, let me explain what is going on here. In the special case that my model is exactly matching the process, okay, and there is no disturbance, this d hat will always be 0. If no model mismatch, no plant model mismatch or process model mismatch and no disturbance, okay. So, in the special case where you got no process model mismatch and no disturbance, this feedback signal is 0, okay. Now, so for the time being, just for the sake of explanation, let me remove this, because this signal is 0 in the special case where there is no disturbance and the process or the model exactly matches the process, okay. Then what I have is this controller. If I look at this part, what this guy is doing is trying to control the first order part of the process, and this first order part can be controlled as tightly as you want. So, you can control, you can tune GC, you can have your Kc and tau I in this GC as tight as you want, okay. So, that gives you a very large gain, and then what you do is the control signal that comes out here, I am calling, let it be u only, this control signal that is coming out here u, your valve or your final control element is moved based on this u, okay, whatever is u, that is the signal that is going to the valve. So, your valve moves, of course, because your valve is moving, output will respond after the dead time and y will show some response. However, notice that because I am using I am moving my control input to control only the first order process, this movement can be as fast as I want, so that the first order part is controlled very tightly. So, in effect what I am doing is I am controlling the first order part of the process as tight as I want, and it is based on that I move the actual valve. And notice that as far as the process is concerned, there is no feedback loop. You see, there is no feedback loop. If my model process mismatch is 0 and if the disturbance is 0, this signal d hat will always be 0. Of course, in practice there is always a slight process model mismatch, and therefore, this output y, let us say I give a step to y set point, let us say I give a small step to y set point. If I give a step to y set point, I would expect that after some time y actually becomes exactly equal to y set point. However, because there is a slight disturbance or because Km is slightly off from K, that means the gains are not exactly equal, this y may not be exactly equal to set point, but it may be close to set point. To drive that error to 0, I need some feedback action, and this is that feedback action that I was talking about, which was rubbed ago. All right. So, because my model is never exactly the same as the process, and because there are ever present disturbances, I have this feedback loop, but nevertheless notice that in this feedback loop, if my dead times are exactly matched or closely matched, the feedback of the dead time is close to 0. So, you see, the problem in a simple feedback loop where I did not have this prediction business was that the dead time was being fed back, and because the dead time was being fed back, I could not use a large gain, and therefore, my control was going to be loose. and in some cases that may not be acceptable. When it is not acceptable, you bring in this Smith predictor business, and what you will get is, if your model is close to the process, you are actually saying that the D signal has got little or no dead time in it, okay? And therefore, you can use a large gain in the PI controller, and that will give you much better tighter control. Of course, the performance of this, when it does not take a genius to figure this out, optional update delivery close, okay. Of course, the performance of this Smith predictor it depends a lot on how close your model matches the process, okay. If and the performance will degrade significantly as the process model mismatch increases. So, there are what is called robustness issues, and the problem with such model based approaches is, if the model is good, this thing is going to work well, you will get very tight control of Y in spite of the process showing a large dead time. However, as the model starts to degrade because your process itself is shifting, then the performance of this loop or this controller, the Smith predictor based controller will actually degrade. And you may actually appreciate this, I have used a large gain in this guy. Now, let us say theta deviates over time, and then what happens is the amount of dead time that is being fed back actually increases. Now, with that large gain in GC, you see my closed loop system may actually become unstable, okay. So, therefore, one of the, what should I say, one of the key things that you have to worry about in model based control is performance degradation, because there is uncertainty in parameters, okay. And there is a whole area that deals with robust control. Your controller must be robust even as theta deviates plus minus 10%, k deviates plus minus 10%, tau deviates plus minus 10%, and so on and so forth. We are not going to cover that, we are just worried about the basic idea. So, this is the basic idea. Now, let us say you have got an inverse response process. So, we have looked at the Smith predictor for a dead time, pure dead time process. Let us say we want to look at Smith predictor for inverse response process, Smith predictor based control, Smith predictor for inverse response process, inverse response process. Well, why do you get an inverse response? Well, inverse response comes because of right half plane zeros in the open loop transfer function. Inverse response is because of right half plane zeros, at least one right half plane 0, right half plane 0 in open loop process transfer function, okay. So, the simplest transfer function that actually can represent an inverse response process would be, for example, Gp is equal to k into 1 minus alpha s, where alpha is greater than 0, yeah, that should do it, divided by, well, let us just make it a second order, tau square s square plus 2 epsilon, let us just say tau 1 s plus 1 into tau 2 s plus 1. This is the simplest transfer function that will give you an inverse response, alpha is greater than 0, okay. what would be the Smith predictor equivalent for this process? You see, the difficulty is coming because of inverse response. Okay. So, my truncated model should be this guy. This is easily controllable. Inverse response is due to this guy. So, the full model is this, is GP. The truncated model is what I have circled in that orange line. Okay. Therefore, the Smith predictor for this process would look something like this. You got your process, it can have a disturbance plus this is your output, this is your input to the process with little more space so that it is clear. Okay, so let us have a decent model there. Okay, so Km 1 minus alpha m s divided by tau 1 model s plus 1 divided by tau 2 model s. So, this is your full model. You take this. So, this is your estimate of the disturbance, assuming there is no plant model mismatch, and what you have is your truncated model is here. What is your truncated model? Truncated model is Km without the right half plane 0. So, just Km over tau 1 model s plus 1 times tau 2 model into s plus 1. So, this is your truncated model, and this you control using a controller, which could be simply a PI controller. I am just saying it could be a PI controller. And of course, because there can be disturbance, you need to feed that back. This is y set point plus. So, this would be the Smith predictor for an inverse response process. Alright. I think that is about all that is to be said about a Smith predictor. Okay. So, these are all model based approaches, and as plant model mismatch increases, what you will have is that the performance of this controller will degrade appreciably, particularly because you are trying to use large gains in this PI controller. Okay. As the model becomes, as the process deviates and there is significant process model mismatch, you would be feeding back through this channel either the dead time or that right half plane 0. Okay. And because the gain here is large, your control system actually may go unstable. So, what is the largest gain that you can use, given that there is so much uncertainty in Km, alpha m, tau 1 m, tau 2 m, and that is something that is there is a lot of theory that goes around it, but basically you try to address this question in what is called robust control. So, your tuning is such that it can handle uncertainty in your process parameters, the gains, the right half plane zeros, and the time constants. Okay. So, that is that. Now, the Smith predictor is a model based approach for a CISO system. We are now going to switch gears and get to what is used a lot and has been applied a lot in industry. In fact, it actually dynamic matrix control. This is another model based control approach which is quite prevalent, extensively used in the industry, dynamic matrix control, and it forms it's one of those, it's one of the techniques of what is called model predictive control. So, your model makes a prediction, and based on that prediction you try and do so many things. Okay. Now, what is model predictive control? Before we get into the intricacies of model dynamic matrix control, there a little bit needs to be said about what you are trying to do in model predictive control. Okay. Let us say this axis is time, this is time. Okay. Right now I am here in current time, this is current time. Okay. I have got a model. I know what I have done in the past. My control input in the past has moved in some way, whether the operator moved it or a controller moved it, it does not really matter, but I have that history with me. Let us just say this is my control input u, the signal that went to the valve. Okay. We are looking at a single input single output system right now. We will generalize it to multiple input multiple outputs, but right now let us just consider a seesaw system. So, I have got my control input trajectory for the past, and I have made it small steps because my controller is sending a signal to the valve, let us say every 10 seconds, every 15 seconds, every half a minute. Okay. So, it is a sampled system. Okay. So, control trajectory is there, my output in response to that control trajectory is showing some movement, and let us say this is where I want my output to be. So, this is where I would like my output to be, and because of disturbances my output was close, it was going there, then I did something, it came close, and again blah blah blah. Right now I am here, this is my output trajectory, right now I am here. Now, because I have got a predictive model, let us just say that it is a predictive model, I have a predictive model, and because the past will have an effect on the future, what I let us say can do is, based on whatever has happened in the past and my current measurement, I can make a prediction of how the output will move if I do nothing. That means, if I do nothing means I do nothing, I keep the control input where it is, this is the do nothing option. Okay. If I do nothing, how would my output move? And let us say that prediction is my output would move this way, it does not reach where it is supposed to reach. Okay. Then the next question is, how should I move my input, my control inputs? If I do nothing, output shows a certain trajectory, and this is actually called the free response. It is called the free response. No control action. So, this is the green line is the free response. Okay. Now, as a controller, I would like that my output should reach the set point as quickly as possible, or alternatively I would like that my output should reach my set point as quickly as possible without the controller having to move the valve too much. Okay. This is just plain in English explanation, we will mathematize this later on. So, if I do nothing, I get the free response. Now, the question is, how should I move my input, my control input? What should I do to my control input? Now, this is a question. So, let us say I want to make 4 or 5 control moves, current, next. So, I have 1, 2, 3, 4, 5. So, let us just say I want to make 5 control moves, including whatever I want to do now, plus over the next 4 sampling instants. So, in these 5 control instants, on these 5 instants, what should I do to my control input so that my output reaches the set point as quickly as possible? That is the question that I am asking. So, what should u future be? What I was saying was, what should my future control trajectory be such that my output reaches the set point as quickly as possible without the controller having to make two large changes in the valve position. Okay. So, what should u future be? That is the question that you are asking. So, that whatever. So, all this actually tells you is I want to make control moves over the next 5, 6, 7 or maybe m. This is called the control. What are the next m control moves that I want to make? That is called the control horizon. Okay. And let us say I am predicting my output over the next p. Let us say I am predicting my output, this is my prediction. Time t equal to 0 is here. Okay. What should I do over, what is my output is predicted over the next p sampling instance including current time. Okay. Not including current time. Okay. So, this is called the, what is it called? This is called the prediction horizon. So, in model predictive control, the question that is being asked is, given whatever I have done in the past, given where I am, wherever my output is right now and my knowledge of what the set point is, what should I do over the next m, what should my next m control moves be, so that my prediction of the output over the next p sampling instance follows a reference trajectory as closely as possible. Okay. I hope this explanation is reasonably clear, and since there are no students, I really do not know if it is or if it is not, but nevertheless there is the control horizon. What should I do over the control horizon to my control input, so that the prediction of the output over the prediction horizon is such that that predicted response matches my reference trajectory as closely as possible. I think that is the basic idea behind model predictive control. Now, depending on what type of a model you use, whether it uses an impulse response model or a step response model, you get model predictive control, or you get dynamic matrix control, or you get model algorithmic control, you also have GPC. We are just going to look at dynamic matrix control, which uses as the predictive model the step response. Okay. Now, getting on to dynamic matrix control, what does it do? It does, what the hell does it do? Well, it uses a step response model. What is the step response model? Your process is at rest. Let us say you make a 1% or delta percent change in your control input. Open loop system, I make a step change to the input and I note what how my output responds. So, let us say my output responds as is typical for chemical processes. This is how my output responds, an S-shaped curve, slow and sluggish response. This sluggish response is sampled every, let us say, I do not know, 10 seconds, 15 seconds or t seconds. Okay, so, it is sampled every so many seconds. Okay. And this is my okay. Let us say the magnitude of the response, that means deviation from rest, is from the state of rest, which is here, is I do not know A1, A2 and so on so forth, and let us say I get here to A n minus 1, and this guy over here is A n n, and beyond A n, you know, the output has reached its steady state, there is hardly any change. That means A n plus 1 is about the same as A n, that is A n plus 1 minus A n is close to 0. Okay. So, we do not need to worry about what happens beyond that. Okay. So, if delta is not 1%, is not unity, then what I do is I multiply or divide by delta, and then what I get is these GI, which are called the unit step response coefficient, unit step response coefficients. And as the name suggests, that is, what is the change in the output to a unit step, that is what the G's are. The I index represents how far away from the step are you. So, G1 would be how much does the output move after one sampling instant given of the step. G2 would be what is the change in the output to a unit step 2 time instants, 2 sampling instants after the unit step has been given, and so on so forth. Okay. So, these GIs are called the unit step response coefficients, and it is using these GIs that we actually predict the output trajectory given past history of moves and whatever moves I want to make in the future. Okay. Now, getting back to this business of control horizons, 89, maybe I need to go to 91. Okay. All right. Now, again looking at my, this is current time, and I want to predict my output k instants from current time. Okay. So, that means I want to predict, the hat indicates, okay, that is what I am looking for. So, what is the output going to be k instants from now? Well, how do you answer that question? To answer that question, let me give you the expression first. You see, first things first, let us say I have a input sequence that looks like this. This input sequence can be looked at as a summation of steps what is the let us see, it can be looked at as a summation of step number 1, then at second time instant you give another step which is of the same or relatively same size. So, the next step looks like maybe this only, about the same size. At third instant the step is again of the same size or about the same size. The fourth instant, the step is negative and about twice the size of whatever the steps were before. So, at the fifth instant, this is my baseline, this is 0. At the fifth instant, let us use, I do not know what color, red maybe. This is the fifth instant or fifth or sixth or whichever instant you want to call it. My step is twice and twice, 4 times of this about, you know, that is a big step. So, you see this input sequence is a sum of all these small steps, right. So, any input sequence can be looked at a summation of small steps, all right. Like we were talking about, any input sequence. So, this is my general input sequence right here, can be represented as a summation of steps, small steps, as is shown here. Okay. Now, in response to these small steps, my output changes. So, let us say I have, let us say the magnitude of each of these steps in the sequence is delta u. So, for example, delta u 0 is the magnitude of the step that I take at current point in time right now. Delta u 1 would be the magnitude of the step that I take one instant from now. So, for example, this is delta u naught, this is delta u 1, meaning the magnitude here, and this would be delta u 3 or rather delta u 2, the magnitude here. This is delta u 3 and this is delta u 4, and so on and so forth. Okay. So, these delta u's represent the small change in position, the small step change in position at an instant in time. Okay. Now, what I want is, given these delta u's, I want to predict what using my model, what should be my predicted output k instants from now. Okay. Now, if I look at my process, the process is, this is my process, I have got the input, I have got the output, and of course, there is a disturbance that is coming in plus plus. Okay. Now, my output would be, predicted output at instant k would be, and I am going to rub this off for the sake of space. Okay. So, well, if this is my process, I want what y hat k would be, given that I know whatever I have done in the past, I know all the delta u's in the past that have been implemented. Okay. There can be changes in delta u at current instant in time as well as in the future. Of course, I do not know what those moves are, but as a function of those moves I can predict y hat k. Okay. So, y hat k would be, since it is a causal system, the contribution of whatever I did just before this, the step that I took just before k at k minus 1, let us say I took a step that was of this size. Okay. Its contribution will be G1. G1 is the effect of a step one instant from now. So, if I am looking at k1 k minus 1, the previous instant before k, what is the effect going to be of whatever I did at k minus 1 would be G1 times u, or rather delta u k minus 1, because G1 is the response if delta u was 1. Since delta u may or may not be 1, I take the multiplication of the two. This is essentially superposition. The response here is going to be the superposition of whatever I have done in the past. What is in the past? K minus 1, k minus 2 and so on and so forth. The response y hat k would be summation G I delta u, and I goes from here, I is the index that is actually determining how far away from k am I. When I is equal to 1, I am looking at k minus I. I am looking at one instant before wherever I desire the prediction, which is k instants from now. Okay, 1 to infinity. Theoretically it will go to infinity, but for all practical systems, if I make a step change now, after 3 time constants or 4 time constants or 5 time constants, my output reaches steady state. So, I only have to go only so many units in time before, not beyond, because the effect of whatever I did long in the long past does not make a difference on now. Okay. So, for example, if I take a small step, my output responds like this, beyond this time there is no effect of. So, this would be for example n. That means g n plus 1 minus g n is close to 0. So, how far in the past do I need to go? How far behind here do I need to go? I need to go n steps. Anything beyond n steps has very little effect. Okay. So, instead of infinity I say n. For the heck of it, let it remain infinity, that is okay. Now, plus, you see, if this is my process, plus whatever is the disturbance at that instant in time. The simplest way to predict the disturbance is to say that disturbance k instants from now is equal to whatever is the estimate of the disturbance now. Okay. This is the simplest model for the disturbance. This is the simplest model for disturbance. There are Arima, Karima, all kinds of other models, but we will look at the simplest for disturbance. Okay. So, the disturbance k instants from now is going to be whatever is the estimate of the disturbance right now. And how do I get the disturbance, an estimate of the disturbance right now? Well, I say that so d hat k is going to be d hat 0, and what is d hat 0? I say d hat 0 is, how do I estimate the disturbance right now? What I do is I take whatever is y measured right now minus predicted y right now. Okay. So, this is what is taken as the estimate of the disturbance right now. Okay. Now, to simplify, to take a look at this, I split this summation into whatever I have done in the past and whatever I need to do, which I do not know. I do not know what I need to do. Nevertheless, so I split it into two, past and future. So, this summation is split into I equal to 1 to k. So, if I move k steps back, I will get to delta u 0. I do not even know what I need to do right now. Okay, I have just gotten the measurement. G I delta u k minus I plus summation k plus 1 to infinity G I delta u k minus I, okay, plus d naught hat. Now, what would d naught hat be? D naught hat would be equal to y measured minus y predicted 0. What would minus y predicted 0 be? Y predicted 0 will be I is equal to 1 to infinity G I delta u minus I. When I equal to 1, I am looking at delta u minus 1, that means 1 instant from 1 instant before current time. I equal to minus 2, that means 2 instants before current time, and the effect of those control moves was G1 and G2, sum it up. Okay. Okay. So, if I substitute this over here, what I get is a minus summation I equal to 1 to infinity Gi delta u minus I plus y measured. Okay. And what this gives me is y predicted k instants from now is equal to this remains summation I equal to 1 to k Gi delta u k minus I plus summation, and now what I will say is, okay, so I is equal to, now what I will say is I goes from 1 to infinity and delta u is minus 1 minus I, sorry, and this would be Gi minus this will be G k plus I. Yep. Okay. My predictor, k step predictor, this is called the k step predictor, k step predictor. Y hat k is equal to summation I equal to 1 to k, what the hell was it here, G k minus I, k minus I delta u k minus I, and this is plus summation G k plus I minus Gi into delta u minus I plus y measured. So, this is my k step predictor. If I write this, if I make this prediction 1 step, 2 step, 3 step, m steps and p steps into the future, what I will get is, so prediction over the prediction horizon, prediction over prediction horizon. Okay. So, that would be y predicted 1, that means 1 step from now will be, further simplify this as, this is the summation of future control moves, the effect of future control moves, and if all the delta u's here are 0, what that would mean is I am not doing anything in the future. Okay. So, this is called the free response. So, what I have is y hat k is equal to, by the way, I can actually, the indexes here are slightly mismatched. Over here the interpretation of I is this index, this is current time, and how far away I am moving is this. The interpretation of I here is, this is k steps, this is current time, and I am moving I steps behind. Okay. In order to get it, if you wanted that the interpretation of I should be deviation from current time, whether in the plus side or in the minus side, then I think this will have to be changed slightly, and that change is what I am going to implement. So, y hat k is equal to summation delta u I, where I is the deviation from I steps beyond current time, and G would be k minus I. Yeah. So, if I is and I would be what? I is equal to 0 to k minus 1. Yeah. Plus this guy G k plus I minus G I delta U minus I plus Y measured. Okay. And here I is going from 1 to infinity, and instead of taking it to infinity, I take it only n steps back, and this capital N is such that you move as far back as is necessary. So, for example, if this is my step and this is what my response looks like, this may be a good where the output stops to change. This may be a good value of n for this kind of an output response. Okay. Alright, so we were looking at the k step predictor, and what we had was, this is the effect of future moves, and if all the future moves are 0, that means all the delta ui's here are 0, there is still a response, and that response is due to whatever we have done in the past, and this is, like I said before, is called the free response. Okay, future moves, and this the name that is given here is called forced response. I don't know what I should do in the future. These are known, this is also known. Okay. So, now the question is, I want to figure out how should I change delta u's. Okay. In order to figure that out, is equal to summation G k minus I delta ui plus f k. I will call this the free response, k step predictor for the free response. Okay. So, y predicted 1 instant from now is going to be G1 times whatever I do now plus predicted free response 1 instant from now. Y predicted 2 instants from now will be G2 times delta U naught plus G1 times whatever I did just previous to the second instant, which is delta U1 plus F2, and so on. Y hat P instants would be, if you have, this is my time horizon, and if this is my current time, I make control moves till here and I make predictions okay. So, this is my prediction horizon and this is my control horizon. So, that means I am making m plus 1 control moves and I am predicting over if this is p, this would be p predictions. Okay. So, y p would be, how much is this distance? P minus m. Yp would be G P. Let's see. I'm not very sure what this would indexing. It doesn't matter. Let's just delta U P plus G P minus m plus 1 delta U P minus 1 plus G P delta U naught plus F free response P instants from now. Okay, so if I write this in matrix form, so let's say this is 100. So prediction horizon is I make y1, y2 and y100. So let us say p is equal to 100, and let us say m is equal to, I make 10 control moves. Let's just say that's 10 means, if m is equal to 10, that means I make 11. So this would be 0, 1 to 11. This is 10. Effect. Okay, so this looks okay to me. Okay, so if I write this in matrix form, what I will get is y predicted 1, y predicted 2, and so on, y predicted what, p will be equal to g1 zeros times delta u naught, delta u1, delta um. What would y2 be? That's actually g2 times delta u naught. So this would be g2, this would be g1, the rest would be zeros. And what would this be? This would be gp, gp minus 1, and this would be g p minus m. Notice that the columns of this matrix, of course this plus f1, f2, the free response prediction. Okay. Notice that the columns of this matrix are the step coefficients, and you are just moving that column down. This is the whole set of step coefficients. This is the whole set of step coefficients. Then this is the set of step coefficients shifted by 1, and and so on and so forth. The third column would be 0, 0, g1 and so on till gp minus 2 and so on and so forth. Okay. Again, this is the step coefficient shifted by 1. Okay. So my predictor in matrix form looks like this. So in matrix form, what I have is y hat predicted is equal to, it's a vector, is equal to a matrix G times the control moves, the vector of control moves over the control horizon, plus the free response. Okay. So this is my predictor in matrix form. This guy G matrix is called, which has got the step coefficients shifted by 1 as the columns, is called the dynamic matrix. This is called the dynamic matrix. Okay. I want to figure out what should I do to delta u. So you see, this delta u is unknown, what I should do over the next m control moves. Now this delta u is unknown, what should I do in the future? How should I move my control input in the future, now and in the future, such that my y predicted minus, there is a reference trajectory that I have, and this I would call the error. E is equal to, how I get the reference trajectory, that's another matter, we'll discuss that shortly. So how should I change my output such that E transpose E, which is the sum of squared of errors, that means the sum of squared of the deviations between the predicted output and the reference trajectory, is minimized. So what I am looking at is minimize over delta u, this guy. Okay. So what should I do to delta u such that my y predicted follows my reference trajectory as closely as possible? In the ideal case, y predicted and y reference should be 0 always. That means my predicted output, ideal control predicted output, is following the reference trajectory exactly. The solution to that is actually, okay, so this can be written as E is equal to y predicted minus f minus y reference minus f, adding and subtracting f. Okay, so then my equation is y predicted minus f is equal to g times delta u. If the delta u's are unconstrained, is delta u is equal to g transpose g. This comes from least squares. I suppose you would have done least squares gt times y reference minus f. So this is called the least squares solution. How do we get it? Please refer to a least squares analysis book. Essentially what we have is, I'm just giving you by analogy. You would have done, you would have seen, if I want to predict in regression, what you have is y is equal to x beta, and these betas are unknown. Okay, and the best estimate for this beta is equal to x transpose x inverse times x transpose y. Well, I have done the same thing here, except that in our case beta is delta u, this is not known, and y is actually this guy. Okay, so I just replace y by y hat minus f, that is all I or rather y reference minus f, okay, because that is what I would like it to be. Okay, so I think this is how you get your delta u's. Okay, I have not imposed any constraints. Typically in practice, what you try and minimize is not the sum of squared errors. What you try and minimize is minimize over delta u E transpose E plus lambda times delta u transpose times delta u. You see, this minimization actually represents, I want, this is close tracking, I want close tracking with the reference trajectory, and this is, I do not want too much to spend too much control effort. That means I do not want to move my valve by too much. So I want to minimize the error as well as the control effort, and the solution to this guy, unconstrained solution, is, if this is the objective function, the unconstrained solution is delta u optimum, the star indicates optimum, is equal to g transpose g plus lambda I inverse times g transpose times y reference minus f. Okay. In practice, of course, you will have to do the optimization is actually not unconstrained. You see, you cannot move in an instant. For example, in one instant you cannot expect that the valve will move from 0% to 100%. You can only move the valve so much. Okay. So there are always constraints. So now what you want to do is minimize over delta u my objective function, which is E transpose E plus lambda times delta u transpose times delta u, such that, or subject to, magnitude of delta u being less than some number, delta u max. Also u, which is the position of the valve, this should always be between 100% and 0%. And what is u equal to? U is actually the summation of all the delta u's. Well, that is fine. Okay. So now this becomes, the solutions that I just showed you were unconstrained optima. This problem is a constrained minimization, and since the objective function is quadratic in nature, that is sum of squares of E and U, quadratic minimization, there are quadratic programs. And what do quadratic programs do? That is a theory in itself and we will not get into that. Those of you who are interested may please look it up. As far as I am concerned, there is an optimizer that will minimize the objective function subject to whatever are your constraints, and that is called QDMC. Okay, so you optimize delta u or you calculate delta u to minimize your objective function subject to a set of constraints, and that is done using quadratic programs. And one of the quadratic, I mean in MATLAB, if you look, there is a command called quadprog. This is actually a quadratic program. All right. Next time what we will do is, right now we have looked just at a single input